In this video, we're going to go over section 5.3 from our textbook, which talks about solving rational equations and inequalities, and then we'll also look at several word problems as well. So first, we're going to start off with solving rational equations, and this procedure here to do so. So the first thing that we're going to do is determine all values for which the rational equation has undefined expressions. So what values of x, or what values of our variable, will make our rational equation undefined. Then what we'll do is we'll clear our fractions by multiplying each side of our equation by the least common denominator of all rational expressions in this equation. And lastly, we'll solve the resulting equation and throw out any values that will make our equation undefined. So let's look at this example here. First step, we want to determine all values for which the rational equation has undefined expressions. So we know, just by looking at this guy here, that if we were to plug in positive 3 here, we would be dividing by 0, so that would be undefined. We also know that if we were to plug in negative 3 here, we would again be dividing by 0, so that would be undefined. Also, looking at this guy here, positive 3 or negative 3 in this case gives us a positive 9. And so we would end up with 9 minus 9, which is also 0. So this tells us that the values positive and negative 3 make this equation, so make the above, undefined, which I'll abbreviate as UND. Now the next thing we want to do is clear out these fractions by multiplying each side of our equation by the least common denominator. Now something to notice before we do that is that the denominator on this side, x squared minus 9, is exactly equal to x minus 3 times x plus 3. Right, when factoring that guy, we'll get this here. So this tells us that this is going to be the least common denominator for all of our rational expressions. So what we're going to do then, and we'll show this. We have x over x minus 3, and then we have 5 over x plus 3. And if we wanted to add these guys together, we would first have to multiply this side by x plus 3 over x plus 3, because our least common denominator is the product of these two. So we need to multiply these to get to that least common denominator on that side. And similarly, we would have to multiply this guy by x minus 3 over x minus 3 to get a common denominator. And then on this side of our equation, we already have our common denominator of x squared minus 9. So we're good on that side. Now, multiplying these guys, we're going to get x times x plus 3 over x minus 3 times x plus 3 plus 5 times x minus 3 over x plus 3 times x minus 3. And we still have 18 over x squared minus 9 on the right-hand side. Alright, so let's continue to multiply this. We're going to get x squared plus 3x. So just distributing this x here to both terms. And then foiling this guy, we know we're going to get x squared minus 9. Similarly, we're going to distribute our 5 to our x and our minus 3 here. So we'll get 5x minus 15 over x squared minus 9 again. We have our right-hand side there. So we now have that our rational equation here is in terms of the least common denominator, x squared minus 9. And so if we multiply both sides of this equation by x squared minus 9, so I'm multiplying this by that. Let's make this a little more clear. X squared minus 9, and then I'm multiplying this side by x squared minus 9. What happens is, since this x squared minus 9 is multiplying this term and this term, we're going to get an x squared minus 9 in the numerator, and we already have an x squared minus 9 in the denominator, so these guys cancel, and these guys cancel. Similarly, on the right-hand side of our equation, these guys cancel. So we're left with x squared plus 3x plus 5x minus 15 is equal to 18. All right, now for step 3, we want to solve the resulting equation. So our resulting equation, actually we can simplify a little bit. We are combining this 3x and this 5x, and we have this minus 15 here. But we can also move this over and subtract, or sorry, minus 15 here, and we can move this over, so we subtract 18 on both sides as well. So we'll get minus 33 is equal to 0. Now it's of the form where we are comfortable solving this guy. So for step 3, we're going to solve this equation, and we'll do so by factoring. We want to find two numbers whose product is equal to minus 33 and whose sum is equal to positive 8. So that'll be x plus 11 and then x minus 3. So this tells us we have x is equal to negative 11 and x is equal to positive 3. Now remember, for step 4, we want to reject any values we found in step 1, so any values that make this guy undefined. We said that was positive 3 and negative 3. And if you notice here, we got a positive 3. So this tells us for step 4, our solution set is only going to include the value negative 11. Okay? And this is because x is equal to 3, it makes our equation undefined. All right, let's look at another example here. We want to find all complex solutions for the following equation here. So we're going to do the same process that we saw in the last example. First, we know that the values of x is equal to 0 is going to make this guy undefined because we would then be dividing by 0. So this makes our equation undefined. Next, we want to multiply by the least common denominator to get rid of our fractions. Well, just by looking at this guy, our least common denominator is going to be x squared. Because we can multiply this by x squared, or sorry, by x over x to get x squared here. And then we can multiply 1 by x squared over x squared to get an x squared in the denominator here. And then in that case, we would have each of these fractions under or over a common denominator. So doing that, we're going to multiply every single term here by x squared over x squared. And then we have 20 over x squared already, so we don't need to do anything to that guy. So this gives us x squared over x squared minus 9x over x squared plus 20 over x squared is equal to 0. And so we're going to multiply both sides of our equation by our common denominator of x squared. And again, since this x squared is going to be multiplying to each term here, it's canceling out all of these guys. Then on the right-hand side, we know that anything times 0 is 0, so we just keep 0 on the right-hand side of our equation. So we get x squared minus 9x plus 20 is equal to x squared. Oh, sorry. It's equal to 0, right? Now what we're going to do for step 3 is solve this equation. So this is pretty simple. We can factor this guy. We need two numbers whose product is going to be positive 20 and whose sum is negative 9. So that'll be x minus 4 and x minus 5. Okay, so this tells us our solution set for step 4 is going to include both positive 4 and positive 5, because the only number that'll make this undefined is x is equal to 0. So our solution set is this here. Now let's look at solving inequalities, solving rational inequalities. So here's our 3-step process for doing so. The first thing we're going to do is rewrite our inequality so that 0 is on one side and there's a single rational expression on the other side. Then our second step is to determine the values that will cause either the numerator or the denominator of our rational expression to be equal to 0. So if the numerator of our rational expression is equal to 0, these are going to be our x-intercepts. And if the denominator of our rational expression is equal to 0, these are going to be the values not in our domain. Okay? So these values are going to determine the intervals that, or these values will split our domain into intervals. Okay. Then for step 3, we're going to use a test value from each interval to determine which values form the solution set, so what we're looking for. So let's look at this example here. We have this rational expression, and we want to figure out for what x values will make this rational expression less than or equal to 0. So the first thing we're going to look at, well, actually step 1 we don't need to do because we already have a rational expression on one side and then 0 on the other. So step 1 is done for us. Now for step 2, we're going to figure out when our numerator is equal to 0. So I'll abbreviate numerator like that. So numerator equals 0 when x plus 1 squared is equal to 0. Taking the square root of both sides, we just get x plus 1 is equal to 0, which then tells us x is equal to negative 1. So when x is equal to negative 1, our numerator is equal to 0. Next, we want to figure out when our denominator is equal to 0. And that happens when x minus 2 is equal to 0, so when x is equal to 2. So, like we said, these numbers are going to split our domain into intervals. So let's imagine our domain as this number line here. We have the real number line, so we have negative infinity over here and infinity here. So we have one number here, negative 1. I'll just put right about there. And then we have positive 2 here, so maybe right about there. So as you can see, these numbers are splitting our domain here into these 3 intervals. Now for step 3, we're going to use a test value from each interval to determine which intervals form the solution set, and in this case, which intervals make our expression less than or equal to 0. Now something else to note here is that we're looking for x values, like I said, that will make this less than or equal to 0. And we just saw that this will be equal to 0 when our numerator is equal to 0, right? Because 0 divided by anything is just 0. So this means this x is equal to 1 here is going to be part of our solution set. So just as a side note there. All right, and like we said, we want to look for test numbers. So we're going to create a table here. It's a little different than the table that is shown in the Pearson PowerPoint slides, but this is how I like to do it. So we have our interval, our first interval is from negative infinity to negative 1. Our second interval is from negative 1 to 2. And our last one is from 2 to infinity. And we're looking at test numbers in each of these intervals. So for this one, for example, I can choose negative 2. This one I can choose 0, and this one I can choose 3, because these are all test numbers within these corresponding intervals. And so what we want to do is plug in these numbers into our rational expression and figure out what we get. So that will be our values here. So plugging in 2 into our expression, we get negative 1 over 4. Plugging in 0, we get negative 1/2. And plugging in 3, we'll get 16. Okay. Now remember, we want to figure out what values make this expression here less than or equal to 0. And so looking at these outputs here, it looks like this will be less than or equal to 0 in this interval and this interval here. So for these intervals. So our solution set would look like this interval from negative infinity up to negative 1, and then negative 1 to 2. Right? These two intervals. But remember up here we said that we're also looking at when this will be equal to 0, and we know that'll happen when x is equal to negative 1. So negative 1 is part of our solution set. This here looks like negative 1 is not part of our solution set. So we'll rewrite this as negative infinity up to 2. Now, as you can see, I have the graph for this function here on the right, and I just wanted to show you what's happening here. So we know that in this region, from negative infinity up to this point 2 here, all of our values are negative. all of these values are less than or right about there equal to 0. And we see that this point here, x is equal to 2, is actually going to be a vertical asymptote, right? Because these guys are not crossing this line here. Now, the reason why we wanted to find the values which make our function undefined or equal to 0, our numerator equal to 0, is because when our rational function is undefined, that tells us where our vertical asymptotes are. And when our function is, or when our rational expression is equal to 0 here, this is where our expression has the potential to change sign, right? So when we're looking at when this equation or this rational expression here is going to be less than or equal to 0, this is when this guy is going to be negative or equal to 0. And we know that when this guy is equal to 0, it's touching our x-axis, and everything below our x-axis is negative, and everything above is positive. So if we're touching our x-axis here, we have the potential to then cross the x-axis into our positive region here. So that's why this point here will split our domain up whenever we're crossing that x-axis into potentially different regions of different signs for our expression. In this case, even though we touched the x-axis, we didn't change sign, and that's totally fine. It won't happen every single time. We can just touch the x-axis and come back down as we see here. But that's the reason why we want to split our domain up into these intervals here. All right, so the last thing we're going to look at are two variation problems. So first we'll start out with inverse variation. So let x and y be two quantities and let n be some positive number. Then y is said to be inversely proportional to the nth power of x if there exists a non-zero number k such that y is equal to this here. So if y is equal to k over x, in this case, our n here is just going to be 1. And we'll say y is inversely proportional to x. So let's look at this example here. We're told that the intensity of light I is inversely proportional to the second power of the distance d. So right off the bat, let's write an equation for this guy. Okay, we say that the intensity of light is given by I, and it's going to be inversely proportional to the second power of the distance d. So if it's inversely proportional to some variable, that means it's going to be k over that variable to some power, right, given by this guy here. And we're told that it's the second power. So we have the distance squared on the bottom. All right, now we're told that at a distance of 3 meters, a 100 watt bulb produces an intensity of 0.88 watts per square meter. So we want to find the constant of variation, which is given by k here, and then determine the intensity of the light at a distance of 2 meters. So we're told that the intensity is 0.88 watts at a distance of 3 meters. So plugging that information into our equation, we get this here. And what we want to do is find this constant of variation k. So we'll do that by multiplying by 9 on both sides of this guy, because 3 squared is equal to 9. So these will cancel. 0.88 times 9 is 7.92. And so that's what k is equal to. Now with this information, this constant variation for k, we can find the intensity of the same light at a different distance here, which is going to be 2 meters. All right, so we get 7.92 divided by 4. So this will be equal to 1.98 watts per square meter. All right. The next variation problem we're going to look at deals with joint variation. So we're going to let m and n be real numbers. Then we say that v varies jointly as the nth power of x and the nth power of y if a non-zero real number k exists such that z is equal to this guy here. Now all this means is that a variable, which is z here, depends on two other variables, x and y, and here some constant k. Okay, and then we can also have that these n and n powers here are just 1 as well. So let's look at this example. We're told that the weight of a can of soup varies jointly with the height and with the square of the diameter. So we'll write an equation for this as well. So I'm going to let W be equal to the weight. So the weight of a can of soup varies jointly. So it's going to have the form of K times two other variables, right? Because it's going to be dependent on two other variables. So in this case, it's dependent on the height and the diameter here. So I'm going to say H is the height and D is the diameter. Okay. Now it looks like it varies jointly with respect to the height here. So we're just going to have H to the power 1 and the square of the diameter. So this will be D squared. Okay, so that'll be our equation for the weight of a can of soup. That varies jointly depending on the height and the square of the diameter. Now we're told a can that is 3 inches high with a diameter of 4 inches weighs 19.2 ounces. With that information, we're going to be able to figure out the weight of a can that is 6 inches high with a diameter of 2 inches. And we'll do so by solving for our constant K here. So plugging in the given information, we have a can of soup that weighs 19.2 ounces, is 3 inches high, and has a diameter of 4 inches. Here we'll get 3 times 16, so that'll be 48. So we'll have 19 times 2 is equal to K times 48. Then we'll divide by 48 on both sides to solve for K. So we'll get K is equal to 0.4. Alright, now with that information, we want to figure out the weight of a can that is now 6 inches high and has a diameter of 2 inches. So the weight is going to be equal to our constant 0.4 times our height, which is 6 inches, times the diameter squared, so 2 squared. So we'll get 0.4 times 24, which will be 9.6. So the weight of that can will be 9.6 ounces. Alright, so that'll be it for this video.